Aloha, everyone, and welcome back to Edit 429. This week, we're going to be focusing in on the one sample t-test. So we'll begin our discussion about the t-distribution, the t-test, by starting with the fact that we're going to begin to explore statistical inference in scenarios where sigma, or the population standard deviation, is unknown. Up until now, we've assumed in our problems and in our textbooks, or in the chapters of the textbook, that sigma is a known entity, that we have that population parameter and we're able to know it exactly. Because of this, we've been able to compute the z-test statistic and conduct hypothesis tests. So again, remember that z-test statistic comes to, or is found by taking our sample mean minus the population parameter, the population mean assumed by the null hypothesis, divided by the standard error of the mean, which is sigma sub x bar. Okay. But in reality, we rarely know sigma. This means that it is much more difficult to compute the standard error of the mean. Now, recall that sigma x bar is equal to sigma divided by the square root of n. So we know that the square root of n is just a function of our sample size. So that's fine. But we really needed this sigma value in order to compute sigma sub x bar. Now, when sigma, again, the population standard deviation, is unknown, we need to add a layer of complexity to our work, which is we need to estimate sigma. Okay. Fortunately, the same general logic of hypothesis testing and estimation apply even when we need to estimate the population standard deviation. So everything you've learned up to this point will continue to be relevant, and we're just adding a new step into this process to be able to get an estimate of the population standard deviation. Okay, so the same general logic applies. Remember, step one was to specify the null and alternative hypotheses, and then to set the significance level, or your alpha. Step two was to select the sample and calculate the necessary sample statistics. Step three, you determine the probability of the test statistic. And step four, you make the decision regarding H sub 0. Okay. So we make our decision whether to reject or retain the null hypothesis. Our new focus this week is to describe the process of testing statistical hypotheses about mu, the population mean, when sigma, the population standard deviation, is unknown. Since sigma is unknown, we now need to estimate it. But how, you might be wondering? Well, you have to reach back to some of your knowledge from the first half of the semester. So you have to go back to what we were doing during our sections on descriptive statistics. And remember that during those chapters, we actually learned how to estimate the sample standard deviation. And it turns out that the sample standard deviation is our best estimate, our best guess of the population standard deviation. Okay, so recall, the sample standard deviation can be found by taking the square root of the sum of squared deviations from the mean divided by n minus 1. So remember, x minus x bar is the deviation from the mean. We're squaring that and adding up all of those squared values, then dividing by n, the sample size, minus 1. And our resulting quantity here, we will then take the square root of that value, and the resulting value is our estimate of the population standard deviation. It's our sample standard deviation. Okay, so let's look at an example here. So for example, let's say we've got data from Professor Coffey's survey on internet use. We've got all of these different students A through J, indicating the number of hours in a typical week that they spend on the internet. And so you can see here, there's a step that's kind of missing when we think back to how we did this in the early parts of the class. So we actually had an extra column here that was x minus x bar, which would give us, 6 minus 9.90, which would give us negative 3.9. And then basically what this table is automatically jumping to is the squaring of this value. So negative 3.9 squared gives us the 15.21. So over here to the right, we have the squared deviations from the mean. And so from this column then, by adding up all of these values, we get the sum of squared deviations from the mean, or also referred to in the book as just this SS value, which is the sum of x minus x bar quantity squared, which gives us a value of 148.90. And again, here, they calculated the x bar by adding up all of these values of x and dividing by n. Okay. So again, to get the sum of squared deviations from the mean, we're going to use this column over here. Now, to calculate our estimate of the standard deviation, we're going to go basically take our square root of the sum of squared deviations from the mean, so this 148.90, which we'll plug in right here, and we're going to divide it by n minus 1, which comes from 10 minus 1, so we get square root of 148.90 over 9, which gives us square root of 16.54, leaving us with a value of 4.07 is our estimated standard deviation in that particular instance. Okay, so the sampled standard deviation is critical for statistical inference that we will be doing for the remainder of the semester. And estimating this, the reason why it's so critical is that it allows us to estimate the standard error of the mean S sub x bar, which looks strikingly similar to what you've been seeing before, which was sigma sub x bar. So here we're looking at the estimated standard error of the mean. And the main difference is that instead of using sigma in our numerator, we're now using S, which is our estimated population standard deviation. So think for a second about what we're really doing here, and we're adding a little bit more uncertainty to our estimate of the standard error of the mean, because we no longer know the population standard deviation. Now we have to estimate it, and there's going to be some sampling variation related to that. Okay, so let's go back to our example. We now have all the information we need in order to calculate this estimated standard error of the mean. So we now can just go ahead and go back to this new formula, which is very similar to what we were working with previously, but now we're going to take S sub x bar equals to S over the square root of n, which gives us 4.07 divided by the square root of 10, results in a value of 1.29. Okay, now that we have that value of 1.29, we're able to run to calculate our test statistic, which we will then be able to use to make a decision about the null hypothesis. Okay, but there's something that has changed, which is we're now using a different test statistic. So up until this point, we've always relied on the z-test statistic. Unfortunately, however, we can no longer use the z-distribution because we don't know the population standard deviation. And correspondingly, we don't know the standard error of the mean, the exact standard error of the mean. As a result, we cannot rely on the z-distribution any longer. So when we estimate the population standard deviation, we compute the sample standard deviation and correspondingly this estimated standard error of the mean, S sub x bar. And when we do this, we need to account for the slightly larger amount of uncertainty in our estimate. And to do that, we need to use the test statistic T, which is a very similar distribution to the Z distribution, but it allows us to account for this added amount of uncertainty. Okay, so just as a quick reminder, which test statistic do you use in which context? Well, when sigma is known, we use Z. But when sigma is unknown, we use the T distribution. Okay, so how do we calculate the T test statistic? Well, it's pretty simple. It's pretty straightforward and very similar to how you calculated the test statistic. The only difference is that now you're using this S sub X bar instead of sigma sub X bar. Okay, so T test statistic is found by taking your sample mean minus the population mean assumed by your null hypothesis divided by your estimated standard error of the mean, S sub X bar. So again, the only difference is that we are estimating the standard error of the mean with S sub X bar. Okay, so from our running example, in order to calculate the test statistic T, or the T ratio, we simply go ahead and plug in these values that we now have. So we take 9.90, which was our sample mean, minus, say, in our null hypothesis, it was about 6.75 was the population mean being tested. And we had our estimated standard error of the mean at 1.90 or 1.29. When we do that, we obtain a T test statistic of a positive 2.44. Okay, now the key difference between the Z and the T distribution. Well, for the Z distribution, we were estimating one statistic, X bar, which we got from our sample, right? From the random sample we drew. Everything else was known. We assumed we knew the population standard deviation, which meant that we knew the standard error of the mean. However, for the T distribution, we have a different scenario. We now are estimating two key statistics. The first one, X bar, from our sample just as before, but now we're estimating S sub X bar, which is our estimated standard error of the mean. Therefore, there will be more sampling variability in the T distribution than in the Z distribution, and this is especially true for very small samples, or samples that have less than 30 observations in them. Okay, so where do we get this T distribution from anyway? Well, there was a guy by the name of William Gossett who worked for the Guinness Brewery in Dublin, Ireland. And he wrote under a pseudonym of Student so as not to get in trouble for a bunch of tests that he was running. And what he discovered was that there's this family of T distributions that he figured out by frequently running small experiments about the quality of Guinness beer in the beer factory. So he wrote under the pseudonym when he wrote about his results as Student T. And so that's why sometimes you'll hear that the T distribution is referred to as either just the T distribution or student's T distribution. You'll sometimes see. Okay, but so what is this T distribution? Well, it's close to the normal distribution, but has slightly wider tails. In other words, slightly taller tails than the Z distribution. So if you take a look, this first curve here, which if you follow, you'll see it actually goes and has the shortest tails here, the tails that are closest to the ends of the, closest to the axis. That's the normal distribution. What Student T distribution shows us, though, is that when sample sizes are very small, when we have fewer pieces of information, there's actually going to be more error in our tails of the distribution. So what you'll see here is this distribution here is the T distribution. And you'll notice that as we go down, it actually gets a little bit further from the axis as we get out into the tails, meaning that there's more area in those rejection regions. Okay, so what this is showing is that when you have many, many pieces of information about it, about the sample, you're going to be pretty close to a Z distribution. But for small samples, when we'll talk about degrees of freedom in just a moment, but when your information is relatively low, so say you only have 4 pieces of unique information, then it's going to diverge from the normal distribution by just a little bit. And we're going to need to account for that because that influences how we conduct hypothesis tests. Okay, so let's talk about characteristics of the T distribution. It's a family of distributions that depend on degrees of freedom. It's wider at the tails, which means that the critical values for t for a given level of significance, so if alpha, say, is 0.05, the critical values for t are actually going to be further out in the distribution. So maybe +2 or +2.02 instead of what they were for the z distribution, which might have been 1.96. So what we're seeing is that because there's these tails are slightly taller, that means there's more probability that can fall in them. So to have a rejection region that accounts for, say, a significance level of 0.05, our critical values are actually a little bit further out from the mean. Okay. So what is the degree of freedom? Well, it's a value indicating the number of independent pieces of information a sample of observations can provide for purposes of statistical inference. So when degrees of freedom are infinite, the t and the z distributions are identical. In fact, even when the t distribution, when the sample size is, say, 200 or 300, they're very, very close. But these two distributions will differ when the degrees of freedom are very small. So when degrees of freedom are 10 or 15 or 8, then it becomes very important to pay attention to the differences between the t and the z distributions. Okay, so how do we actually do this? How do we work with this table? Well, how do we find critical values using the t distribution? You guessed it, we're going to have a new table in the back of the book in the appendix just behind the old z table. And you're going to go ahead and use that table to help us figure out important critical values that we might need for conducting hypothesis tests. So just as a bit of background on how to read this table, what you'll see is that the student's t distribution gives us two sets of information. So the first part references whether or not you're using a one-tailed or a two-tailed hypothesis test. So you've got 0.20 all the way down to 0.01, and you've got basically trying to see if this is assuming that you're using a two-tailed hypothesis test. Now, if you're looking at the values in the area of one tail, then you want to use these corresponding values, which means that if you're looking at a one-tailed hypothesis test, you want to be sure to be looking at these particular values in the table. So let's break that down. Let's say you had you were looking for a significance level of 0.05, you had a two-tailed test, you would come to this particular column and you would look for these critical values. And the other key piece of information you would need to know would be the degrees of freedom in your particular context. But let's say you had a significance level of 0.05, but instead we're doing a one-tailed test. Well, rather than looking at this column here, you would need to go over here and look at this particular column. Okay, but I think we'll get to that a bit more in our slides. So the key thing is that this table specifies the type of rejection region, either a one-tailed or two-tailed test, and two, reports the critical values for the rejection regions depending on the degrees of freedom. Okay, so again, this first set of information tells us whether we're using a one or two-tailed test, and this second set of information provides the critical values. Okay, so let's look carefully at table 13.2, and let's look at the instance where we have 9 degrees of freedom, and we have, basically a situation where we're saying we want to have an alpha of 0.05, and we have a two-tailed test. Well, in that case, we would go to, okay, area in both tails has to add up to 0.05. We've got 9 degrees of freedom. So our critical values are going to be plus or minus 2.262. And let's say we changed our focus and we wanted to go all the way to the point where we said, instead of looking at a significance level of 0.05, we actually want an even higher or a smaller level of significance. So 0.01 is our alpha. In that case, we have to split the area between two tails. So it'd be 0.005 and 0.005 on either end. But we would again come down to the degrees of freedom equaling 9, and we would get that we're actually going to need critical values of 3.25 and negative 3.25. And you can see that illustrated here on this t distribution, which shows that we've got negative 3.25 and positive 3.25 here, and everything beyond that has an area of 0.005, and everything beyond the 2.262 and negative 2.262 is the area of 0.025 on either side of the distribution. Okay, so that gets us to how we find the critical values using the t-distribution. You can, again, refer to this. Let's say you want to look at anything else, you can refer to the back of the book and find a whole other set of potential critical values. Okay, now we can test our hypotheses. So using the t-distribution, we can determine critical values, which we can use for conducting statistical inference. Remember, we've taken all of these steps. So we're looking at the t-distribution specifically because we now have to estimate the population standard deviation, sigma. So when we do this, we refer to this type of hypothesis test as a one sample t-test. Okay, so what are our steps? Well, the steps for the one sample t-test are, again, one, we specify our null and alternative hypothesis and set our level of significance. Step two, we select the sample, calculate the necessary sample statistics, which in this case are going to be X bar, S sub X bar, and the t-test statistic. The third step is we're going to use that table we were just looking at to determine the critical values of t. And then if our t-test statistic is more extreme than the critical values of t, we're going to go ahead and reject the null hypothesis. But if it's not, we'll go ahead and retain the null hypothesis. So we'll make our decision in step 4 about whether to reject or retain the null hypothesis. Okay, so let's talk through an example. So let's say we have our null hypothesis is mu is equal to 6.75. And our alternative hypothesis is that it does not equal to 6.75. So that should immediately tell you we're working with a two-tailed test. And now we set our significance level of 0.05. So we're going to have 0.025 and 0.025 probability on either side of our distribution in both of the tails. So 0.025 in each tail. Now we're going to go to step 2. And let's say we've calculated our X bar is equal to 9.90. Our estimated standard error of the mean is 1.29. And our t ratio is positive 2.44. Now we go to our table and we say, okay, we're looking at degrees of freedom is equal to 9 because we know degrees of freedom is 10 minus, or is our sample size n minus 1. So we're going to have degrees of freedom is equal to 9. And we're going to be able to find that, for having 0.05 in both tails, we see that the critical values are plus or minus 2.262. Okay, now all we have to do is compare what we found in step 2, this positive 2.44, with our critical value of positive 2.262. Since the test statistic is more extreme than the critical value, we reject the null hypothesis. Okay, so again, let's visualize this example. So we have our t distribution here. We've got our 2 rejection regions out beyond either more extreme than negative 2.262 or larger than 2.262. So any of this shaded area to the left or of the lower critical value and to the right of the upper critical value are our rejection regions. And we know that our sample mean of 9.90 gives us a test statistic of a positive 2.44. And that falls in the rejection region. Okay. Now, if we go back to our sample, but we change something. So what's different about this example now? Well, we made one modification, which was that the population mean is going to be greater than 6.75 in our alternative hypothesis. So when we specify that, that indicates that we're now using a one-tailed test. We've kept our same level of significance. So how does this impact our hypothesis test? Well, it's going to give us a different critical value than we had before. So again, our X bar, S sub X bar, and T ratios remain the same. Nothing has changed there, but our critical value is different. So now we go to the table, we look up degrees of freedom is 9, and this time we look for the column that has 0.05 in one tail. And we find that the critical value is going to be 1.833. So we go back to our test statistic and we see that it's a positive 2.44. Our critical value is positive 1.833. Since the positive 2.44 is more extreme, we say we reject the null hypothesis. So here you can visualize it once more. We have our T distribution here, our wider rejection region, because now it's all the potential rejection area is in one tail, but our sample mean hasn't changed, and our T ratio hasn't changed. And so what we see is that we'll continue to reject the null hypothesis. So pulling this sample that gives us a sample mean of 9.90 indicates that we find pretty strong evidence against a null hypothesis, indicating that the population mean is 6.75. Okay, so the key takeaways. If the t-test statistic falls beyond a two-tailed critical value, it will also fall beyond the one-tailed critical value. For the same level of significance, the critical values for the t distribution are larger than the critical values for the z distribution. Okay, finally, a note on the assumption of population normality. The t ratio follows student t's distribution exactly if the population distribution is normal itself. But the central limit theorem that we've learned about previously helps us to assume that the values from table B are accurate when n is reasonably large. In other words, greater than or equal to about 30. For small samples, it makes sense to examine the underlying distribution of the variable of interest. Okay, so now let's move into confidence intervals when sigma is unknown. This is a pretty straightforward extension to what you've learned previously about confidence intervals. So we can construct confidence intervals when sigma is unknown. And we're going to do it in almost exactly the same form as we did before, except there's going to be one difference. Rather than relying on the z distribution, we're going to use the t distribution, which basically accounts for the fact that we're estimating the sample standard error of the mean. So the general rule for a confidence interval for mu, the population mean when sigma is not known, is here. So it's going to be our X bar plus or minus the t critical value times S sub X bar. Okay, so to do this, if we go back to our example, we plug in our values from the running example. So we have X bar is equal to 9.90 plus or minus our critical value times our estimated standard error of the mean, which gives us 9.90 plus or minus 2.92. So we now compute the upper and lower limits, which would be 6.98 to 12.82. Notice that your null hypothesis value of 6.75 does not fall in this confidence interval, which again gives evidence that you would reject the null hypothesis based on what you're finding here. So once more, the main general rule here is that instead of using z, we're now using the t distribution, and instead of using sigma x bar, we're now using s x bar, s sub x bar. Okay. So that's all we've got for this week, and I look forward to seeing you all next week to talk about extending our discussion of statistical inference even further. Have a great week, everyone.